Welcome back to the morning show. It is 6:48. If you're looking for a little summer science fun, well, the wise guys got a little soap and a little water in mind for you.
We've all done some sort of this experiment, blowing bubbles, but this is a little different variation. We're talking about the science of just how it all works.
That's right, but it's good, clean fun.
It smells good in here, actually. You can smell the soap.
Now, last week we talked about surface tension, right? And I had some water here, and we floated little metal things on the water.
Right.
And we talked about the fact that if you look at the skin of the water, it's like a little film that forms on top, because the molecules of the water that are at the surface kind of hold on to each other. Right. They link together, and so you get this little skin on top. And if you focus in on this cup over here, if you can do that real quick, you'll see what I was talking about last time, that in this cup, the water is sort of bulging over.
Yeah, the water is actually kind of on top of the cup there.
Yeah, exactly. The water is sticking out. Now, the interesting thing is, if I get a little soap on my finger and I touch this thing,
oh, there it goes.
spilled
right up here. And it's not just because you put a lot on. It was barely a drop.
Right. And in fact, all I did was put a little on my finger. What happens is the soap actually reduces the surface tension.
Okay.
Because the soap sort of disrupts all these water molecules as they're hanging onto each other. So the question then is, how come you can blow soap bubbles? If the soap makes surface tension smaller, you'd think it would be harder to form bubbles. But in fact, that's not the case. What you have with a mixture of water and soap, which is what I have in this can, it's this Dawn dishwashing liquid, I believe, and some water mixed together. I'll put the recipe on my website. What happens is, if you try to blow a bubble with this water, it evaporates very quickly and it pops. And also the surface tension is really too big, and you can't sustain a bubble with such a lot of surface tension.
Okay.
But if you put a lot of soap in there, what the soap does is it kind of coats the layer of water so it doesn't evaporate, and so you can actually form a bubble that lasts a little bit of a while. Okay? And so we've all blown bubbles, so let's try this here. And in fact, I have this little gadget here, which is kind of silly.
There it goes.
Okay.
Lots of bubbles.
Okay. Now, what you notice with these bubbles is that they're all the same shape.
They're all round.
They're all round, right. And the reason for that is that these membranes, they try to arrange themselves in such a way that you have the smallest area, surface area, for the enclosed volume, okay? And so that way, it's just like if you have a rubber band, it doesn't bend sideways when you stretch it. It's always a straight line. It's the same with a film. It tries to make itself the smallest possible surface, and a sphere is the smallest possible surface that you can enclose a volume with, okay? And so it likes to do that. Now, what if you try to fool the soap bubble
into making a shape?
Into making a shape. So, here, I'm making a mess here. I'm going to put this in here. This is just a little wire hoop, and I pull it out. And if you zoom in on that, you can see that you get a very interesting shape. So the soap, what the film does now is it tries to sort of arrange itself in such a way that it's the smallest possible area.
Right.
Okay, so
that's happened there. Wow.
And it sort of happened there. I've got another one here, which is this funny-looking sort of, I'm sure there's a name for this. Okay. And see there,
almost
how
a
pretty that is?
cube or something.
You get these very flat sides.
Now, if you blow this, though, what would happen? Would it just pop?
Let's find out.
Some bubbles come off.
Some bubbles come off, right.
Bubbles.
So there's some,
round,
but they're round, yes.
Ooh, that's a big one.
So what you can actually do, what's kind of fun, is if you take a surface and you get it like this, the top of this jar has a sort of concavity to it.
Right.
And I put a little soap in there. If you just take a straw.
Oh, look at that.
You can blow interesting bubbles. And in fact,
so again, the shortest possible distance to just make this.
So it makes this sort of a dome. And what you can do is you can play around with this. If you get a soapy straw, you can actually poke it right through the bubble without breaking it, and you can blow bubbles inside the bubble.
Bigger. Is there a limit to how big it can get? Oh, you're blowing multiple bubbles.
Right, and so you can try to get interesting shapes on the inside, like for example.
But that object has to be covered in soap as well, right? So I shouldn't ask you to talk while you're
you're blowing bubbles. So if you look in here, though, you can get these funny shapes because I've blown the bubbles inside the bubbles there, okay? And this is, you can play around with this stuff at home. In fact, if you get your finger kind of soapy, you can stick it right into the bubble without breaking it, okay? Because it doesn't disrupt the soap clings to your finger as well as it would cling to itself. So you can go in there and you can play around. And it's kind of a challenge. The challenge, I challenge any kid out there to do this. Blow enough bubbles on there that in the middle someplace you have a square bubble. You can actually do that.
And that can happen.
Wow.
What's coming up next at 7:25?
Okay, so we're going to have some other bubble things. We have some fluorescent bubbles. We're going to light them up with a black light that looks very cool. And we're going to look at light diffraction through the skin of the bubble, which is very interesting too.
All right, wise guy Matt Sellen talking about the science of bubbles today. We'll get back to this at 7:25. Now we need to check the weather with Robert.
You guys are all bubbly this morning and cheerful.